Let's lots of requests for stuff mostly to do with circuits. So I thought I'd start with this little puzzle. So it starts with what's hopefully a mark giveaway for 2 marks, and then there are 3 marks where some thought is necessary. So let's just make sure we can collect the mark giveaway marks. Can we remember the truth table for a NAND gate? I hope so. I hope we can remember this part of the truth table. But can we remember the rest of it? Do all shout at once. What goes here?
1, 0.
Excellent. For part B, we are asked, show how to construct a NOR gate from NAND gates. But at this point, we should guess that we're going to want to build a whole bunch of stuff from NAND gates. It might just be good to build all the usual things. So let's just remember how to build NOT. How do you build NOT from NAND? Do all shout at once?
Tie input together?
Yes, types input, yeah. Duplicate the input. So now we've got NOT, we should be able to build AND. Just by negating the output. How about OR? How do we build OR from NAND? We negate the inputs. This is just stuff. That's basically De Morgan's law. This is stuff that you should basically know. And then how do we build NOR? We negate the OR. So you'll notice that I always am happy to reuse components that I've already built in order to build more stuff. That's not merely permitted, that's encouraged, because it allows you to work at a higher level, just make it clearer what's going on. If you were to draw this NOR gate out made from 4 NAND gates, it would be much harder for me to see and for you to see that you've got the right answer. Whereas here, it's a negated OR gate. You can just see that, so you know you've got it right. And I can see it too. Okay, so hopefully that's two marks collected. Now we're on to the fun part. A traffic light is controlled by a 2-bit counter with phases red for 0, red and amber for 1, green for 2, and amber for 3. So it's a perfectly ordinary traffic light. Construct the circuits which control each individual light. Be sure to label the 2 inputs with their place values and the outputs R for red, A for amber, and G for green. Okay, so those are some words, but we are being asked to build some circuits. So we need to think carefully about how to approach this. But first of all, can we identify for the circuits we've been asked for, what are the inputs? I mean, do we know what all the word means? Do we know what a 2-bit counter is? A 2-bit counter is a circuit which produces a signal that is 2 bits wide, representing a 2-bit number, and as time goes on, it will send the signal for 0, the signal for 1, the signal for 2, the signal for 3, and then back to 0 again. It will count through the 2-bit numbers. So it produces 2 bits that represent the 2 place values in a 2-bit number. And that's what the question refers to, place values. So we're told the mappings between the numbers 0, 1, 2, and 3 and which lights are on in the traffic light sequence. So we're going to get as an input the 2 bits of the number, and we're going to have to deliver as outputs whether or not each light should be on at that stage. So a good move in the first instance, even though we're not asked to do so explicitly, is simply to translate the words into a truth table that characterizes the behavior we want. So, let's draw a truth table. What do you think we should label the inputs? Remember, the inputs are the 2 bits of a 2-bit number. What would it be useful and meaningful to label these inputs? 1s and 2s, preferably in this order. Yeah? And the outputs are supposed to be the controllers for the 3 lamps in the traffic lights. So what should we label them?
R, E, and G.
Yeah, red, amber, and green, easily abbreviated to R, A, and G. Okay. So now we can fill in the inputs, which, as you can see, count in binary from 0 up to 3. If the people that were talking at the back are annoying you, feel free to throw something at them, preferably something quite heavy. If they're not annoying you, then that's fine. I'll just carry on being annoyed down here. Right, so we're told red for 0, red and amber for 1, green for 2, and amber for 3. So can we identify when the lights are on? Let's look at the red light. Is it on here? Which phase are we in? We're in phase 0, and that's the red phase. So that's 1. Actually, maybe we could go horizontally instead. Should the amber light be on in this phase?
No.
No. Nor the green light. Okay, how about phase 1? Which light should be on?
Red and amber.
Red and amber, but not green. How about phase 2? Just green. And how about phase 3? Just amber. Okay, so having gone to the trouble of drawing this truth table, we are now in the business of building the circuitry. So we have a choice. We could build one circuit with 2 inputs and 3 outputs, or we could build 3 separate circuits, each with 2 inputs and 1 output. And I don't care which you do. Here, my guess is it'll be easier to do 3 separate circuits. So, any suggestion for how to build the circuit for red? It's not 2s. Yeah? So you see, I mean, this is an optimization. We can see we want to detect whether we have 0 and 0 or 0 and 1. That's the same as saying we want 2s to be 0 and we don't care what the other one is. If you happen to spot that, that will make life easier. So we know that. So we've already shown how to make not. So there's your red. How about amber? It's exactly a copy of 1s. So that's even easier. All the hard work is in green. Any suggestion for how to build the circuit for green? Yes, we want to detect exactly this bit pattern. So we do the usual thing, we write down the bit pattern that we want to detect, and then we turn the 0 into a naught. And them together, and then this circuit will detect exactly this line of the truth table. That's the only line of the truth table where we want to get a 1 out, so that is plenty for green. Everyone see the methods? First of all, translate the description of the problem into some truth table. Apart from anything else, that makes it easier to spot familiar stuff, like that red is not 2s, like that amber is a copy of 1s. If it's there in front of you in a truth table, you're more likely to see it. But for green, we stopped being clever and we fell back to the method for building a detector for a specific bit pattern. Everybody okay with this so far? Great. Last part of the puzzle. Keep the old truth table. Is as ever with a last mark, requires a bit more thought. It says, there's no reason why the red phase should be numbered 0. Any assignment of numbers to phases will do, as long as the drivers see the same cycle of phases. Show that by choosing a different phase to be numbered 0, the control circuitry can be constructed with just one NOR gate. So let's figure out what we're being asked here. You can see we've started with phase 0 meaning red. Now what's important is that the phases go in order red, red and amber, green, amber, back to red. And what we can't do anything about is that our 2-bit counter goes 0, 1, 2, 3 and back to 0. So we've got to map one cycle to the other, but that doesn't mean that red has to be 0. Red could be anywhere in the cycle, as long as the next thing in the cycle was red and amber, and the thing after that was green, and the thing after that was amber. Yeah? So the question is, could we reorganize things more neatly if we chose a different coding of the cycle? That's basically to say, if you like, you can see that once you decide which number is red, or which if you fix one point in the cycle, if you decide which thing green is, for example, then all the rest has to fit into place after that. So there's only one choice, there's only one degree of freedom, is to fix one number to one light pattern, and then the rest has to follow. And we're told that as a result of this, we're going to have to make use just one NOR gate to do all 3. Now, what can you figure out about this? This is where some deduction comes into play. And you can get quite far with it. We have one NOR gate to do all 3 signals, and you'll notice the signals are all different from each other. Red, amber, and green. They don't have this. They're not the same pattern. So if you only get one NOR gate between the two of them, between the three of them, you know the other two have to be wires. So that's one clue. The other thing it might be useful to remember is the truth table for a NOR gate. Can we remember that?
Slide the page up.
It's a 1 here, and then zeros elsewhere. So, so what did we notice? Twos, sorry, the red is determined basically in our old setting, it's determined only by twos, and amber is determined only by ones, but green needs information from both of them. Yeah? So, if you look at NOR, you can see, and what's more, green is on, I'll zoom out slightly, green is on only at one point in the cycle. So you can tell that no matter what the cycle is, green is not going to be a wire. Yeah? If green was a wire, it would be on twice in the cycle. It would be connected to twos or connected to ones. What does that tell you about where this NOR gate is going to get used? It's going to be used for green. What does that tell you about which number should be used to represent green? Yeah, the number that is detected by a NOR gate. So let's see if we're lucky. If this is twos and this is ones, we try to figure out how that should be green. So what happens to R and A, right? If 0 is green, what's 1? Amber. And if 1 is amber, what's 2? Sorry, that's amber. Yeah, if 1 is amber, what's 2? Yeah, 2 comes after 1, red comes after amber. Whoops, yes, amber. I'll get that right eventually. And if 2 is red, what's 3? Red and amber. Are we happy? Yeah, we can see that red is now a wire. What about amber? It's a wire from ones. And we deliberately engineered that green would be a NOR gate connected to both. Okay, so there was a bit of deduction to be done there, and it's the sort of thing that might happen. I'm not shy about asking you to deduce things you haven't deduced before for the last mark in a question. So you should expect that sort of thing to show up from time to time. But the important thing is to learn to use truth tables as things that are going on. So ways to see what's going on. So here, the key for us was partly to exploit the fact that we had a hardware budget which told us that some things had to be simple. And then to remember, crucially, that NOR is a detector for one particular bit pattern. And the crucial move was making the bit pattern that NOR happens to detect the bit pattern that we wanted to detect. So it's a bit of backwards reasoning. Instead of saying, here are the bit patterns, detect the ones which show up, I'm instead saying, so build the right detector. I'm instead saying, here's the only detector you've got, fix the bit patterns so that it works out that way. Okay, so is that fine? Hoping it's moderately useful. So I could do another logic question, or I'm very happy basically for noisy people to shout what they want. I've got arithmetics and I've got clocks as well here.
Clocks, memory, correct?
Yeah. Shouts first gets.